This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
All right, hello, and welcome to another episode of Design Safe Radio. So excited to have you here today. And we have Pedro Fernández-Cabán, who is an assistant professor in civil and environmental engineering at Florida A&M and Florida State University down in Tallahassee. Welcome, Pedro. Good to have you.
Thank you for having me, Dan. It's a pleasure.
I'm super excited to chat with you today. Your background is not where you are currently, but has a really exciting piece of machinery that I can't wait to talk to our audience about, because I've seen it in person a couple of times, and it is pretty mind-bogglingly amazing. So let's talk about your research first. You are especially interested in low-rise buildings and the roof systems on those and helping them be resistant to hurricane winds. So can you give us a bit of an overview of your research? What are low-rise buildings? Why is this important?
Yeah, so again, thanks for having me, Dan. So essentially, wind engineers, we typically try to divide high-rise buildings versus low-rise buildings, primarily because the wind action on the structure and essentially what we're interested in looking at is different. Mm-hmm. In our case, we're focusing on low-rise buildings, and specifically, we're looking at roof loads. And then typically, when you're looking at trying to quantify the roof pressures, roof forces, wind forces on the roof, they're typically what we call negative pressures or suction pressures. So those are the ones that generate uplift. So when we're looking at over in the news, for example, you see a lot of roof failures where basically you see uplift happening. So those are the critical forces that typically govern the wind design on low-rise buildings primarily.
So when you say low-rise buildings, you're talking about like a typical home or most businesses or like a Walmart or a school, and not things like apartment buildings and skyscrapers and stuff.
Correct. So yeah, typically low-rise building, it consists of residential housing, one-story, two-story buildings. So for example, commercial industrial buildings that are 1-2 stories are typically considered low-rise buildings. So typically those are the ones where we see roof failure happening and essentially governing the wind design of those types of structures.
Great. Well, as someone who currently is in a low-rise building, I thank you for what you're doing. So great. So we've kind of categorized the space that you're playing in, the playground that you're playing on. So you're doing some experiments now at the really amazing University of Florida Boundary Layer Wind Tunnel, which is one of our two NARI wind facilities. And they've got a really amazing piece of technology that's fairly new there called the flow field modulator, which sounds like something that Marvin the Martian would have invented. It's pretty amazing, and it's right over your head. Can you tell me what this is and how it aids your experiments?
Yeah, so and actually I was quite impressed with it. It's also really loud.
It is really loud.
Oh yes.
It sounds like an angry swarm of bees.
Yeah, so you can definitely hear it and you can feel it when you're there. But and actually we're currently, as we speak, conducting wind tunnel tests at the NERI site there at the University of Florida. So the flow field modulator is a unique instrument, and what's unique about it is it gives us the ability to control the large-scale turbulent gust structures that we see, for example, in hurricanes and large-scale synoptic wind events. So these are wind events of long duration. So hurricane would be an example of one of those types of wind conditions. And us wind engineers have had some difficulties trying to simulate the large-scale gust structures in wind tunnels. And then the flow field modulator allows us to impart these larger, we call them eddies, but essentially those are turbulent gust structures that could impact the wind forces, let's say on the roof of a low-rise building. So that's what we're trying to simulate physically in the wind tunnel.
So a typical wind tunnel, and even Florida's wind tunnel before this, you just get a big straight blast of wind for as long as you want, right? Mm-hmm. But an actual hurricane doesn't do that. It changes a lot. You get swirls, these eddies, you get changes in, different directions of wind, even as the hurricane goes for a long time. it changes through that time. Is that kind of what you're getting at?
Correct. So basically, hurricane winds, for example, they bring multiple a spectrum of eddies. So they have smaller eddies, larger eddies. So in the wind tunnel, for example, for decades we've been able to reasonably well simulate the smaller eddies using, well, in Florida at UF they have the terraformer. So the terraformer can essentially simulate the smaller eddies quite well. So those eddies are generated by primarily mechanical turbulence from the Earth's surface. Now, the flow field modulator, we call it the FFM, then that instrument can impart the larger eddies. So then we can get a better spectrum of eddies that we can simulate in the tunnel, which would approximate, it would be a better or improved representation of what's happening in real life.
Yeah. And this machine is amazing. It's what, like 350 individual propellers, like drone propellers in these 3D printed tubes that kind of looks like a honeycomb.
Right. So there's it's hard to count them, and there's too many, but essentially there are 319 cells. Each cell has propellers, and essentially we can modify the RPM, so the velocity in which those propellers are spinning. We can control that with good accuracy, so that we can essentially modulate essentially the gust structures that we can generate with it.
Yeah, they're pretty amazing. I was visiting Florida when they were first putting it together, and I got to just stand in front of one of those cells. It's really powerful. I think you can add up, I can't remember if it's like 40 miles an hour plus or minus, is something like that for each cell.
Oh, yes. So essentially each cell, what we're trying to impart on the flow is fluctuation. So we're trying to create fluctuations of the velocity, and we can rapidly change the fluctuations and control them relatively well. And I was used to running traditional wind tunnel experiments without the FFM, and I mean, they're pretty quiet, but the flow is typically comes out, the upwind of, let's say, the terraformer comes relatively constant, pretty quiet. And yeah, so these large scale fluctuations, they're as I mentioned earlier, they're loud, but we've run some preliminary tests earlier this year, and it looks to be working quite well for what it was designed for.
Yeah, and you can because you can individually program each of these 319 cells, you can have the wave of pressure go across or up and down, or any combination that you want in real time. It's really amazing.
Correct. Yeah, typically we try to change the velocity fluctuations vertically. So we stratify them vertically. So we have rows of cells, and each row we can assign a different, let's say, velocity fluctuation, and we can change it as we go up, and we can also do that laterally. So we have a lot of versatility as far as the wind field that we can generate.
I'll have to find and see if we can put a link to this in the show notes. Oh yeah, I do have a video. Yeah. I've got a video of a couple of these cells that we'll send to our awesome podcast editing team, and see if we can put a couple of links in there for people to see what this kind of looks like on an individual basis, plus some way better videos that Florida's put together since the
True.
Because you kind of have to see it to believe it. I mean, the picture that you got behind you is great. But yeah,
it doesn't do justice.
It doesn't do justice. If you happen to be down in the Gainesville area, they're always open to people visiting. So anyway, flow field modulator is excellent. And now we get on to your research question here, which is looking at kind of what do we do about this problem? How do we change these low-rise buildings with some innovative roof system geometries that help alleviate these lifts, the suction forces that you mentioned? So for the non-wind engineers in our audience, can you kind of give us an example of some of these different roof geometries? And when the project is complete, do you expect you'll have some practical suggestions for architects and builders of how to deal with these challenges?
Right. No, that's a good question. So for this particular project, we have two main goals. The first one is that large-scale turbulence generation that I mentioned earlier. The second one is looking at how we can sort of alleviate or mitigate or reduce the wind effects, specifically on the roof of low-rise buildings. Now, there's been some wind mitigation strategies for roofs that are currently existing. So for example, parapets, when you look at parapets, so parapet is essentially a protective wall that goes around along the edge of the roof of a low-rise building. So those have multiple functions, but one of them is to reduce the suction pressures that we were talking about earlier. Now you can get creative and you can optimize and enhance the geometry of, let's say, a parapet to sort of confuse the flow and simultaneously being able to reduce the pressures on the roof. Typically, the highest suction pressures occur near the edge and on the corners of the roof. So if you are able to sort of change the structure of the flow so that you can sort of redirect the flow and lessen the effect in those areas, that can go a long way.
Yeah. For really long time listeners of the show, all the way back in episode, maybe 3 or 4, we talked to Dr. Rindam Chowdhury from FIU about a system they developed there that actually captures the energy at the edge of a parapet and turns it into electricity. It was really cool.
Right.
So when you talk about some of those creative solutions, you can get real creative with that.
Right, exactly. And going back to sort of differentiating between high-rise and low-rise buildings, there's also been techniques in order to mitigate wind effects by enhancing the geometry. Low-rise buildings, as you mentioned, FIU has done some work to try to mitigate wind loads on low-rise structures, but there's definitely a lot of ground that could be explored in that particular research area.
Yeah, and especially doing it in a way that captures the existing, building inventory as well as new construction, and solutions are different for each one. And this gets from research into development and practice, but there's economic concerns, there's cultural concerns, there's just the hassle of putting something else on your building. It's like another thing.
No, definitely. I mean, we definitely don't want to reinvent the wheel. So if we can design or come up with some innovative design that could be implemented to existing low-rise structures, but also these would be technologies that could be incorporated potentially to future structures.
Yeah. So let's say we're at the end of your project and we're talking to our friends at the NSF about how amazing it went. What are some of the really great results that you're expecting to see over the next little while you're working on this with your team?
Well, specifically, we want to one of our main goals is to sort of link the wind field that we're generating with the assistance of the flow field modulator to how effective these wind mitigation strategies are for the roofs. So we can develop a roadmap where we know that for certain wind conditions, and let's say if you're in a particular location, geographic location, where the terrain is different and your wind field is going to change, and that could potentially affect the wind mitigation strategy that you would use for your roof, then we can sort of give some guidance in that regard to practitioners and engineers. And with all that information, we can basically provide recommendations. And so, for example, if for a particular low-rise structure situated in, let's say, in front of the water, so that will be more of marine exposure, so the turbulence properties are going to be different there. So then we would make a recommendation that would be different from, let's say, if you're in a more built-up suburban area. So those are sort of the things that we're looking at.
So how kind of a follow-on question here that we didn't have in our original thing, but I'm thinking, how does a practicing engineer find this research that you're doing? Like, how do you communicate these things? Is it through code changes? Is it sending out emails to lists? Like, how do you go about communicating this?
Yeah, so what we call the tech transfer, technology transfer, and giving this information to practitioners and engineers is critical for us. Typically, we as in academia, as academics, the publications, peer review publications is one way, but also there's a lot of my colleagues and wind engineers. They're very heavily involved with wind load provisions, updating wind load provision, for example, wind standards such as ASC 7. So being able to get this information and transfer it so that we can implement it, let's say in future versions or editions of building codes is critical.
Mm-hmm.
That's something that would once we get the results, once we finish a project such as the one that we're working on, that would sort of be the next step so that we can see the impact, the real impact of the project.
So it's a mix of kind of short-term, publications into journals and things like that, and then more longer term, like updating a building code is sometimes a 10-year process, or up to anyway, depending on what part of the cycle also, you're in.
Right. And also a big part of NERI is design safe, which we might talk about it later on. Also being able to share the data and also share the data in a way that engineers and practitioners can understand. So interpretation and being able to organize and structure the data so it's easy to understand. It's also critical, and that would also be a contribution of the project.
Yeah. And Bill Holmes, if you're listening, this is where our network coordination office team is really good at this. We have a tech transfer committee. You're probably aware of that. But for those who are listening who may not be, like, this is one of the things that we do is talk to amazing people like Pedro and say, hey, what you working on? Like, how can we tell people about it? And guys like Bill Holmes and the rest of the tech transfer committee have those relationships with practicing engineers and engineering firms who would be interested in it in various regions, and know how to talk to them in ways they can understand, so that you can keep doing what you do and we can do our thing. And so you don't have to worry so much about doing all of that yourself.
Right. Exactly.
Cool. So I went down that rabbit hole for a little bit. I always get really excited when we talk about tangible real world things, but let's back up and get slightly back into the theoretical here. So you're not just doing fantastic physical experimenting, but you're also looking at combining previous wind tunnel data along with the data that you're generating from your current experiments through machine learning algorithms and computational fluid dynamics, CFD, one of my favorite things. For those who aren't wind engineers or nerdy former mechanical engineers like me, how do you combine these elements to estimate wind forces?
Yeah, so I first would like to say that my background is experimental. So my main, I guess, relative expertise would be wind tunnel experiment physical testing. As far as the machine learning component and the CFD, the computational fluid dynamics component of the project, what we're trying to do is sort of leverage all the data that we collect in the wind tunnel. So in the wind tunnel, we're limited as far as how many scenarios we can test. So we're time limited. So we know that we can change the wind direction. So we know that we don't know, let's say in a hurricane, where the wind is going to be coming from. So we have to test a set of wind directions, then a set of different terrain and turbulence conditions, upwind turbulent conditions. So we don't have time to run everything in the wind tunnel. So this is where machine learning can come into play, where a machine learning algorithm, which would be essentially data driven. So we would train the machine learning with the wind tunnel data that we have and we collect, let's say at the UF NERI side, and we can sort of fill in the gaps. So for example, we didn't test a certain wind condition in the wind tunnel. Machine learning can sort of give a reliable prediction based on the training data that was provided.
So you can essentially teach a computer to predict what a wind tunnel test would give you data-wise based off of the data that you're feeding into it.
Correct. And typically what we do is we have experimental data and we can divide the data into training data. So that would be the data that would be used to train the machine learning algorithm. But then we would have a subset of data from the wind tunnel that would be test data. And that data was not seen by the machine learning algorithm. So we can use it to see how well the machine learning algorithm can predict those results, which we have. So then there's some validation component there that we can use.
Great. So in a simplistic sense, you're asking, you give the machine a problem like, okay, what is 1 + 1? You know it's 2, but the machine doesn't. And you've designed a program to add numbers together. It adds 1 + 1 together. And if you get 5, you've got to train it to do something differently. But if you get 2, it's accurate.
Correct. And typically how accurate your algorithm would depend on how well you design the machine learning algorithm. So there's some parameters that you can tune with your machine learning algorithm that would enhance or improve the predicted capability, as well as the inputs and the outputs that you are providing to the machine learning algorithm. So there's some tuning there, but
so as a primarily experimental scientist, how are you learning how to do machine learning?
Yeah, so collaboration is a big part. We work with computer scientists, and we know our limitations. Right now, also there's some tools that are more user-friendly that could be used by researchers more broadly, and you don't have to be a computer scientist, but typically what we do is we bring our strengths, and we know that we're limited, and if I'm a wind engineer, I can work with a computer scientist, and they're the machine learning experts, and we can exchange information to solve a problem. But that's a big part of it, and sort of knowing what your contribution is, but at the same time know that you don't know everything. So
yeah, which kind of highlights our rounding third into home last topic here is just the beauty and the power of being part of this NERI network, which does have some really world-class computer scientists involved at the Sim Center with their simulation and modeling tools, as well as University of Texas, the Texas Advanced Computing Center. They've got their new Frontera supercomputer, which I can't even begin to describe how crazy powerful this thing is. But through the Design Safe portal, you've got access to that. So can you talk about some of those aspects, the how we're sharing data and processing that on Design Safe and working with the tools developed by the Sim Center?
Yeah, so what's unique and interesting about the NERI is that the Sim Center, for example, like you mentioned, and then we have the Texas Advanced Computing Center at University of Texas. And let's say if I'm running experiments in the wind tunnel at the University of Florida, all these facilities are connected. So for example, once I collect data in the wind tunnel at Florida, that data could be uploaded automatically to Design Safe, for example. And then that data on Design Safe, I can run simulations or process the data using the high performance computing and the Frontera cluster. So all these resources from NERI are interconnected, and you can use all of them and to sort of speed up your analysis and your processing, and at the same time compare your results. One, you mentioned CFD, computational fluid dynamics, which we are currently also running some CFD simulations in the Frontera cluster, which can significantly speed up the simulation time.
Yeah, I mean, to like put it in perspective, how fast that system makes this, like compared to like a more like your desktop computer, it would take weeks, maybe months.
Yeah, so we take advantage of parallel processing and being able to use multiple computers simultaneously at the same time. So let's say you have a CFD simulation that it could take in a single laptop, it could take months or a year or years potentially. And if you have multiple processors in using the HPC, that is reduced to a matter of a week, essentially. So you can cut the time from a year to a week. So some of these simulations take a long time. So,
oh yeah, it's just to kind of give the listeners a perspective of Frontera. It's the fastest academic supercomputer in the world and the 19th most powerful overall. Like,
yes,
it is crazy powerful. It's like I don't even know how to describe it other than that. It's just bonkers how fast it is. The amount of computing power available for researchers like yourself is pretty amazing. They've got 8,000 computing nodes. So it's basically like having 8,000 laptops hooked together,
right.
With funky amounts of data processing along with it. So yeah, it's a pretty amazing system to have when you're looking at really complex problems. Like a computational fluid dynamics CFD problem is very computing resource heavy. Yeah, I mean, you know this. It's basically looking at all the individual little wind particles and how they interact with each other and how they bounce around and interact with the terrain and the building and jiggle and rotate around each other. That's a lot of math.
Oh yeah, definitely. And when you're looking at problems like the ones that we're looking at, where you're trying to quantify the roof loads on a low-rise building, if you run a CFD simulation to be able to capture those peak forces that are acting on roof systems, the resolution of your CFD simulation has to be so fine that that increases the time it takes to run the simulation exponentially, essentially.
Yeah, because it sounds like you're also combining the CFD with a finite element analysis, like looking at the structure itself and how the different pieces of the roof system interact with each other and the surrounding environment and the rest of the structure and how that changes and the forces and the stresses and the strains on all of that stuff.
So
that as well.
Yeah, so CFD essentially would provide you with the wind forces on, let's say, the skin or what we call the building envelope, and then those loads eventually are going to be transferred to the structural system, which that's where FE finite element analysis comes into play. So that would be more the structural analysis. So you would get the wind forces from CFD, and then you would transfer those forces to a numerical finite element analysis. So
it's really important to highlight how we've talked about the importance of collaboration between disciplines here, of making sure that you as a wind engineer speak in a language that a structural engineer can understand, and using data that they can use in their analysis of the rest of the structure after you've done the experiments and analysis on the effects on the envelope.
Mm-hmm. Yeah, so being effective in communicating your results is a big part of us in academia. We don't want to be the only ones that understand our results. We need to be able to share it with people that can actually benefit from your findings, and that's a critical component of our job for sure.
Yeah, I think that's probably one of the benefits of being in kind of the hazards space, is it's more tangible than some other areas of science. Definitely. Because we've all seen hurricanes, and if you've lived in the southeastern United States or even up the eastern seaboard, you've experienced them and kind of can wrap your head around what that looks like, rather than if we're talking to a theoretical physicist, it's a bit harder to wrap your head around that.
Oh yeah, no, it's definitely relatable and it's tangible. You can feel it, you can experience it, and depending on where you are in the country. But the hazards, if you're on the West Coast, you have seismic, earthquakes, and then Southeast and in the Midwest, you have tornadoes. So hazards are just everywhere.
Yeah. Well, Pedro, thanks for being here today. This has been a really enlightening discussion, especially for those of us who are really into fluid flow dynamics and all of that. So really appreciate your time. Where can folks follow along with your research as you're doing your experiments and starting to publish your data?
Yeah, so Design Safe, we actually are planning on disseminating some of the data that we are currently collecting in the wind tunnel. So hopefully some point later this year, we're going to be publishing some of the data, and we should complete all of our experiments by the end of the year for sure. But definitely keep an eye on Design Safe. Definitely would be one of the go-to places as far as resources for the data sets that we're collecting and that we're curating and putting together. So
great. We'll make sure to post some links if we can find a link to your project specifically in the data set there. And thanks so much. We really appreciate it, and looking forward to seeing what's next for you.
Thank you, Dan. Thank you for the opportunity.
Thanks for listening to today's episode of Design Safe Radio. Be sure to like and subscribe on whatever platform you happen to be listening to this on. It really helps people find our show. Thanks to our amazing sponsors, the National Science Foundation and the NARI Network Coordination Office, which is award number 2129782. Big thank you to Marty LaChance, our guest booker and topic researcher extraordinaire, and Raquel Ruiz, who is our video and audio editor. I'm your host and NARI Facility Scheduling and Operations Coordinator, Dan Zahner. We'll see you in the next episode. Until then, stay resilient.